We've seen how to solve a homogeneous system. Now let's consider how we might solve a non-homogeneous system. A non-homogeneous system can be written as a homogeneous system plus a non-homogeneous part, y being a vector function with n components, g being another vector function, the non-homogeneous part of this equation with n components, and let's assume an initial condition y of t0 equals vector y naught. Okay, the homogeneous equation, as we've seen, will typically have a solution set, and I've just done 2 dimensions here just to keep the notation simple, but there's nothing that restricts this to just a 2-dimensional system. Okay, this could be n-dimensional, then we'd have n members of the solution set. In any case, we have a solution set y1, y2 with wt not equal to 0. That makes this a fundamental set so that we can write down our fundamental matrix psi of t equals y1, y2. Now, this fundamental matrix is itself a solution to the equation. Psi prime of t is equal to your p of t matrix times psi of t. And what we're going to try to do is we're going to try to find a matrix, much like this fundamental matrix, that solves this equation. And it's going to turn out that that's actually fairly easy to do. So, we're going to let u of t, now I'm being inconsistent, I've got u1 through un. This would just be a u1, u2 if it went with the notation I have here where I'm restricting this to a function of, well, to a system of 2 equations, basically. This would apply to a system of n equations. It'll apply to this if n is equal to 2. So in general, we find a function u of t, though, such that whatever our dimension and whatever our fundamental matrix, that the function, the fundamental matrix phi multiplied by the u vector is a solution to the original equation with the initial conditions, non-homogeneous, and everything. And this is just very similar to what we did before. This is a variation of parameters. And you can, if you understand the variation of parameters method that we developed previously for single equations, it's not difficult to see why we call this a variation of parameters. Okay, we're just trying to find a parameter function u, which has a bunch of components, each of which is a function of u. So we're trying to find a parameter vector, which consists of a set of parameter functions that satisfies this equation. That will form a particular solution. Adding that particular solution to our general solution is going to give us the general solution to the equation, and we can apply the initial conditions. Now actually, in this case, we're going to just do an integration that incorporates the initial conditions, but it comes down to the same thing. So to begin to apply the variation of parameters, what are we going to do? Well, we're going to plug this solution back into this equation. That's very easily done. We first have to find an expression for the derivative of this function, but that's easily done. We just apply the product rule and we get psi prime of t u of t plus psi of t u prime of t. For the moment, leaving off the t's, we understand that everything in the equation is going to be a function of t. We can write the non-homogeneous equation as psi prime u plus psi u prime equals p psi u plus g. Now, matrix multiplication is associative. Plugging this function into our equation, we have p times psi u, but that's the same as p psi times u. And what do we know about p psi? Well, p times psi is psi prime, because psi is a solution matrix to the homogeneous system. So it follows that we have psi prime u plus psi u prime equals psi prime u plus g. And that's real progress, because we've got psi prime u on both sides, subtracted off, and we're just left with psi u prime equals g, so that, well, I wasn't going to write it all out, but if I take psi inverse of both sides, we conclude that u prime is just psi inverse g. So in what I think is a very slick manner, we find a solution matrix, or a solution matrix for our non-homogeneous function. Of course, we're going to have to integrate psi inverse g, and we'll look at what that entails in the next clip.